Hello, so here is the first video, the third for chapter 6, but the first video for section 6.2, and we're talking about the normal model, the generalities of it in this video. So this is a curve, this probability density curve is a normal curve, and you notice that it has like a bell-shaped, and a population that is represented by a curve that looks like this, a normal curve, is said to be normally distributed, or to have a normal distribution. So visualizing the normal distribution, or model, this shows the height for a sample of males, and you can see that it's symmetric and unimodal, so you can use it. You can model it using a normal distribution, so you can just overlay this curve and it should be fairly good to approximate stuff with, using like doing analysis on this data. So talking more about the normal model, it's good if the distribution is unimodal, if it's approximately symmetric, and it's approximately bell-shaped. So you see up here it's got like a shape of a bell. It could be fatter, it could be thinner, it's still got a shape of a bell. And the normal distribution is also called Gaussian, named after Frederick Gauss. So the properties of a normal curve, the population mean, or the mean, determines the location of the peak. So looking down here, the mean here is 0 for both of these, so it's located, the peak is located right here on the x-axis at 0. While the standard deviation measures the spread. So this standard deviation is much more, has this distribution much more spread out than this one, where it's really thin because its standard deviation is only 1. And then, so talking about this one, the location, they have the same standard deviation, but they have the same like spread or range per se, but the locations are different because their means are different. So this one's 0, so at 0 is the peak. For this one, the peak is at 5. And to talk, when we talked about measures of center, mean and median of a normal, so for symmetric distributions, they're equal to the mode. And the mean and median, we know, are equal to each other in a symmetric distribution data set. So these normal curves show the distribution of the heights for men, this red curve, and for women, this blue curve in the US. They're both normal, you can see, and they have some overlap here. But this mean is located around 65, while this mean is located around 70 inches. No, the women's is more like 63 inches. So notice that the spread of each curve is about the same, but the centers are different. I just mentioned that. So they have the different means because they have different locations of the peak, but the same standard deviation because they have the same spread. So mu stands for the center or mean of the distribution. This funky looking symbol, sigma, stands for the standard deviation of the distribution. And these are interchanged, what mu is interchanged for x bar, and we know that that's this sample mean, and s is the sample standard deviation, while sigma is a population standard deviation. And then you can see up here, again, it's showing larger standard deviation, more spread out, smaller standard deviation, thinner. And the area under both of the curves up here are 1. So remember that. So this means that n parentheses 6 comma 2 means that the normal distribution, it has mean of 6, mu equals 6, and the standard deviation is sigma equals 2. So you can see that represented up here. So the area under the normal curve above the x-axis and to the left of x equals 4 represents the probability x is less than 4 given that you have a normal distribution of with mean 6 and standard deviation 2. That's all that's saying. But so basically, to simplify it, the probability of x is less than 4 is the same as less than equal 4 because it's a continuous distribution. So do you remember the empirical rule? 68, 95, 99.7. So 68 fall within 1 standard deviation, 95 fall within 2 standard deviations, and 99.7 fall within 3 standard deviations. And so how we could draw that? 7 tick marks. Right here's the center. -1, -2, -3 standard deviations. 1, 2, and 3 standard deviations. So here's the mean. Add and subtract the standard deviation, label each mark, draw a bell curve, and you don't have to label the vertical axis. And if we wanted to find the probability of x less than 4, we shade underneath to the left of it because it's less than 4 on this normal curve. So this can tell standard units or z-scores. So this is a little bit of a review. The z-score of something is x minus x bar. Well, in this case, when we have the normal distribution, the x bar and standard deviations are changed with mu and sigma. But it's still basically the same formula. And remember, this tells us how many standard deviations from the mean that observation x lies. Repeating this again, just remember the z-score is the number of standard deviations. The data value of the observation is above or below the mean. So if x is a value from a normal distribution with mean mu and standard deviation sigma, we can convert x to a z-score by using a method known as standardization. And the z-score of x, we know this, z equals x minus mu divided by sigma. Or back in chapter 2, mu was x bar and sigma was just s. So if we wanted to figure out how many standard deviations a woman that we took a woman who was 67 inches from the population, well, we know that their mean was about 64 inches and their standard deviation is 3. Plugging it into the z-score formula, we have x minus mu divided by the standard deviation sigma. 67 minus 64 divided by 3, because 67 is our observation. Our mu is 64 up here, and divided by 3, that was our sigma, our standard deviation, and this equals 3 divided by 3, which is 1. So the standard normal curve is just the normal distribution with mean 0 and a standard deviation of 1. And so z-scores that have been converted from a normal distribution follow a standard normal distribution because we just standardize it using the z-score. Again, n parentheses 0, 1 just means it has mean 0 and it has a standard deviation of 1. So the standard normal distribution, there's something in Canvas, but to talk about this more generally, there's a table that gives the area to the left of a certain point. So the probability of z less than or equal to z is the area under the standard normal density curve to the left of z. So this table like this is posted on Canvas. So all these numbers, so right here is a z-score for right here 0, 0, 0. So to the left of it, 50% of the data, because this is, all these numbers are the amount of area to the left of it at this point. So let's just say z was 0.62. Well, here's the 0.6, and then this is just 0.60, this is 0.61. Now this is what we're looking for, it's 0.62. Area to the left of z would be 0.324. Okay, so how would we find the area to the left of z equals 1.26? So we could think of a normal distribution being drawn out, and kind of like this. Okay. So let's just say we have a normal curve like that, and we're looking for z, which is 1.26. So we're concerned with what's the amount of area that this red scribble contains. Well, on Canvas, there's something called, under Chapter 6 module, there's something called the z-table, the normal table. So if we wanted to find the area to the left of it with a z-score of with 1.26, well, we have this. So we found the row of 1.2. Now let's just go over. So this is 1.20, 1.21, 1.22, and then we stop right here. This 0.8962. That's the area to the left of the of z at 1.26. So you can see it illustrated again here. The 1.2 row, here's the 0.6 column, that's 1.26, and I showed you this on your PDF that's on Canvas. So here's another standard normal table. There's only one table to find the probabilities of a z-score and to the left of it, and it's always so z-score always standardizes the normal distribution, and that's what this is illustrating. Alrighty, I hope that made a little bit of sense, and hopefully when we do more examples it starts to make a lot more sense, and then it'll be a little bit more complex, because then you'll be asked to, what if we wanted to find the probability from here to this upper z, so from A to B, how would you do that? And we'll talk about that in the next video.